We're going to continue with logarithmic differentiation. Last time we learned that the derivative of ln of x, or ln of the absolute value of x, is 1 over x. Today we're going to learn how to use this derivative along with the log rules to differentiate some functions that we otherwise wouldn't be able to differentiate. Just a quick review. Find f prime of 3 for this lovely function. Well, remembering that the derivative of ln is 1 over x, along with the chain rule, we're going to get this guy. 1 over, leave the inside the same. And then we're going to multiply this by the derivative of the inside. That's actually going to be minus 9 sine of leave the inside the same times the derivative of the inside. And if we wanted to write this a little bit nicer, then we could write this as 4 minus 18x sine of x squared all over 4x plus 9 cosine of x squared. And then, of course, we would plug in x equals 3 and get, I'll just do it out. Fine. 4 minus, was that 54 sine of 9 over 12 plus 9 cosine of 9. Weird. Right, anyway, that's what we get. Now, remember our log rules, right? Log of a product is the sum of the logs. Log of a quotient is the difference of the logs. And also, log of an exponent is that power times the log, or that exponent times the log, okay? So consider a function like this, right? That is not something we're used to seeing, because we know how to take a derivative when x is in the base, and a constant is in the exponent. We know how to, well, we don't really know how to take a derivative when a variable is in the exponent, and a constant is in the base. And we certainly don't know how to take a derivative when an x, or variable, is in both the exponent and the base. That's very, very weird. So there's a process for doing this. It's a little bit drawn out, but it's very formulaic. You do the same thing every single time. You take the ln of both sides of the equation, y equals f of x, right? So we get ln of, I guess you could say the absolute value of y equals ln of the absolute value of x to the sine of x. All right? And just straight up do it, right? Then what you do is the reason we did this is so that we could bring down the sine of x. So we have that ln of the absolute value of y equals sine of x times ln of the absolute value of x, right? Because we could bring it down. That was the log rule. I think it was number 4. Okay? Next up, we implicitly differentiate. In fact, sorry, let me just emphasize the fact that we are using a log rule here, right? That these two things are equal, right? Anyway, we're going to implicitly differentiate, right? Take the derivative of the left, take the derivative of the right. Now think about it. What's the derivative of the left-hand side always going to be? It's always going to be 1 over y dy over dx, right? Which is good, right? Because we want to be solving for dy over dx, right? And now we have to take the derivative of the right-hand side, and note that we have a product rule in this case. Derivative of sine, which is cosine, leave ln of x alone, plus sine of x, take the derivative of ln of x, and we get that. Right? And now all we have to say is, well, we're not solving for 1 over y dy over dx, we're solving for dy over dx. So we just multiply both sides by y, and then substitute y equals x to the sine of x, right? So I'm going to be a little bit lazy here, copy this. Multiply this by y, and if there were no way to represent this all in terms of x, well, then we'd be done. But of course, we know that we can just resubstitute y equals x to the sine of x. And that's our answer, right? So believe it or not, the derivative of y equals x to the sine of x is this big ugly thing. And I know that doesn't look very meaningful, but I do just want to briefly show the similarity between this and e to the x, right? Because the derivative of e to the x is e to the x. The derivative of x to the sine of x is x to the sine of x times a bunch of stuff. So, like, there's some sort of similarity there. Not saying we could have predicted it, but, like, I don't know. It makes sense, is what I'm trying to say. All right, next up, let's derive the derivative of a constant c to the x using logarithmic differentiation. Okay? So if we let y equal c to the x, well, then that's going to imply that ln of the absolute value of y equals ln of the absolute value of c to the x, which, using the log rules, equals x times the ln of the absolute value of c. And this might look weird, but ln of the absolute value of c is a constant and x is a variable, so I'm going to put it first. Next up, we're going to take the derivative. Right, we're going to implicitly differentiate. We get 1 over y dy over dx, as we always do. And on the right side, well, the x goes away and the constant remains. So we get dy over dx equals ln of the absolute value of c times y, which is ln of the absolute value of c times c to the x. So the derivative of 3 to the x is ln of 3 times 3 to the x. Yeah. Next up, we're going to prove the power rule for realsies this time. If you remember, when I derived the power rule, I showed it only for natural numbers, right? 1, 2, 3, 4, 5, 6, etc. You can use it, and of course 0 can, you can easily show that. You can use a trick with the quotient rule to show it for negatives, so we really know it for all integers, but we don't actually know it for decimals, square roots, blah, blah, blah. I just told you it worked. Here's why it works. We're going to let y equal x to the n. X to the n, where n is just any number, any constant. Well, that implies that ln of the absolute value of y equals ln of the absolute value of x to the n, which equals n times ln of the absolute value of x. Implicitly differentiate, we get 1 over y dy over dx equals, well, let's think. N is a constant, so just keep it along for the ride, times 1 over x, right? And that equals n over x, right? If we want to just simplify it a little bit. I think it's a little bit nicer to write it that way. And then this implies that dy over dx equals n over x times y, which is n over x times x to the n, right? Because y equals x to the n. That's what we started with. Right. Just highlight that bad boy. Bad boy, right? Okay. And then let's simplify that one more time. And we're going to get nx to the n minus 1, right? Because n divided by x is nx to the minus 1. So sure enough, the power rule works for all values of n, whether it's an integer, or fraction, or just a non-repeating decimal. It always works. Pretty cool, huh? So anyway, let's do a little bit of practice. Find y prime for each of the following. Well, we're going to actually, sorry, we can't just do it straight up. We have to do ln of the absolute value of y equals ln of x to the x, which is x ln x. Implicitly differentiate, and we get this guy equals 1 times ln of the absolute value of x, right? Because the derivative of x is 1, plus x times the derivative of ln, which is 1 over x. Simplify this a little bit to get this. And then I'll just continue this over here. dy over dx equals ln of the absolute value of x plus 1 times y, which is x to the x. And that's our answer. All right. Now, for number 2, you might be wondering, is the power of x inside or outside the square root? Turns out it doesn't matter, because its multiplication and exponentiation are commutative. So anyway, we'll just assume it's, I don't know, inside. Probably looks a little bit nicer. This would be ln of the square root of x to the x. Let's just say it's on the inside. Again, it doesn't matter. You could put it on the outside, you'll get the same thing, because it is the same thing. Right? And then this is the same as 1/2 ln of x to the x, right? Because the square root is just an exponent. But wait a minute. The x is just an exponent. So you actually get this. And then anyway, this implies that 1 over y dy over dx equals 1/2 ln of oh, actually, I guess I really should be saying absolute values, but maybe not really, because we're talking about the square root, which is always positive. Anyway, whatever. 1/2 ln of x plus x over 2 times 1 over x. Clean that up a little bit, which we always should. And then we get as our answer dy over dx equals... wait, what does it equal? Well, it's going to be all this times y, which is this guy. Okay. I'll do one more example. This is going to be ln of the value of cosine of x to the x. Bring that bad boy down. Take the derivative implicitly. And we get, well, it's going to be 1. Yeah, I like that. 1 times ln of cosine of x. And then we take the derivative of this guy. And cleaning it up, we get ln of cosine, of the absolute value, I guess, of cosine, plus, and you could write this as, or I guess you could say this is minus x tangent of x. And then that implies that dy over dx equals ln of cosine minus x tangent of x times that. And we're done.